I'm just going to focus on how to use brain signal, well, brain, more or less neural signals, because the brain boundaries are kind of like not really very well defined. Is the spinal cord, for example, a part of our brain, etc.? So let's say neural signals, how to use them for stroke rehabilitation. So if we go into the different elements of a neural interface, we get to the neuromodulation possibilities, which is modulating the nervous system or its function based on recording and stimulating it. So if we check how many ways we can interface with the nervous system, we realize that there are many different options, about 6 probably, which could be in terms of magnetic stimulation or mechanical, or I mean I'm saying stimulation, but recording obviously, mechanically also, like ultrasound for example, thermal, chemical, we know all the neurotransmitters, electrical obviously, and recently optogenetics, basically by means of optical means. So if we take a look at the neuroprosthetics timeline or history, we realize that it's been there for a while, so it's nothing new, but it just changed a little bit over time. So we look at the first developments of what we could call like the first FES, for example. It would be the pacemaker. It was actually commercially available in '58, so it's kind of like a while ago. Then we just saw the eruption of the cochlear implants. Later on, DBS. We've seen today something about DBS options. In visual prosthetics was actually in 2013, the first company, second side, first implants. And let's see where we're going, maybe motor or cognitive neuroprosthetics. What we see is actually that the market is huge, which means that there will be a pull from companies, and actually it is happening right now, as Facebook, for example, has a new initiative to build up brain-computer interfaces for communication. And also Elon Musk is actually investing quite a lot of money in a new company called Neuralink, and based on rehabilitation. He doesn't say exactly what kind of, or assistive technologies, what kind of clinical picture, or for what exactly, but we know that there are billions right now invested into that. So if we go back to neural signals, what they are and what we can actually record from them, we can just simply go for the more economic and easy to use and more well known, which is the electroencephalography, basically from the scalp signals, and EMG from the muscles. And this is normally used, and it's actually makes sense to use them right now because it's cheap, and it's kind of like there's a lot of literature showing us what we can do with those signals. And just as a short example of what a brain-computer interface is, or a neural interface, you can record activity on the different levels of the brain, different depths. That would actually result in different signals, and the signals would look a little bit different, but it doesn't matter, you just use signal processing. After that, you get something out of that signal, you interpret that signal, and you have a control signal that you can use to basically, for example, communication, controlling a wheelchair, or a prosthetic arm. But this is all based on visual feedback, or until now it was based on visual feedback. Nowadays we're starting to see some efforts to like proprioceptive feedback by means of, for example, electrical stimulation. This work was done here actually in Belgrade by some colleagues of the faculty here and Technalia in Denmark also, together with many colleagues in the world that are trying to sometimes stimulate also the cortex so that they can feel it. So if we look at the different options that we can have, this is a slide that summarizes quite well what we can do in terms of non-invasive using near-infrared spectroscopy, optical method. You throw light in and then it reflects out, and you can measure that, and you see how the blood uses the oxygen. You can use the EEG, the well-known fMRI. And if you go to the other side, more invasive, we have here the DBS electrodes, but also there are different options like ECOG, electrocorticography, which is actually intracranial EEG. And then we have intracortical electrodes, which are like super small electrodes that get into the cortex and give you signals. Obviously, that means a different resolution in terms of signals, right? So EEG has a very good temporal resolution, but the spatial resolution is not that great. And if we compare that, for example, with ECOG, obviously it's implanted, so better resolution, and the time resolution is pretty good. If we go to fMRI, for example, here, The problem there, although it has a very good spatial resolution, is that the time resolution is not that good. So somehow we need to adapt to the clinical problem that we have, or the solution that we want to generate. We need to be aware of these problems, and we need to design it properly, meaning that if I want spatial resolution, then I know that there is a compromise between time and spatial resolution. This graph summarizes quite well the different options. In here is like more more special resolution, but temporal resolution is not that great. So if we focus now onto motor recovery using neural interfaces, and what is the principle behind it, or at least what is the hypothesis that we're just working with, we see that we are basically using instrumental learning, operant conditioning, right? And this is based on Hebbian plasticity. So how does that work? Normally, I send signals from my brain to the muscles, I see my movement, I feel my movement, and with that, I start playing when I'm a kid, and I'm starting to try to put the star into the star hole, etc. And by learning processes based on error learning, reinforcement learning, and other kinds of learning, I end up inducing some plasticity, some mechanisms that basically generate connections, and by those connections are reflexes and skills being attained, and then I basically learn how to use my nervous system for a visual motor task. But what happens if I have a lesion? And this lesion could be at the spinal cord, or it could be at the brain, like for example a stroke. So what happens is basically that those signals actually don't reach the muscles, or if they pass, they're just super small, not to elicit a movement. So what do I see then? In a healthy person, I see these signals coming back to the muscles, going back. But in a lesion, what happens is that the muscle activity, it's not there, or is very, very small. So I cannot move anymore. So what do we do if that happens? Well, we have the option of using a neural interface. So basically recording the activity at the brain and bridging the gap with the closed loop neural interface that actually would provide feedback into the arm, for example, in this case, using an exoskeleton. So I record the activity in the cortex, I interpret it, I know when the guy wants to move, and I move the hand with an exoskeleton. While doing that, what am I doing? I'm closing the loop. And what happens if I close the loop and I have a task, a functional task? Well, I'm using instrumental learning. I'm just giving the option to the patient to use again instrumental learning and operant conditioning, and therefore I expect to generate some plasticity and some connections again. I'm not talking about neurogenesis, but maybe axonal sprouting. Who knows, but maybe we can use silent pathways at least to recruit them and be able to recover function. So that is the hypothesis that we're using in the neural interfaces and stroke rehabilitation. The background of stroke rehabilitation and why is that so important, it is very clear, but let me just summarize it here. So there is 15 million new cases per year worldwide of strokes, and 50 million of them suffer permanent disability, which means medium, moderate to severe motor impairment. And generally, especially for those severe impaired, the physiotherapy or the mechanisms or methods that are out there are not really sufficient to recover function. So that's where, why not, we can come up and use neurotechnology and combining several devices like exoskeletons, functional electrical stimulation, transcranial magnetic stimulation, I think you've heard that already this morning, and brain-machine interfaces, why not, just to try to assist in that recovery. So just to have an idea of how much does that cost, for example, to the healthcare system. This is normally in the severe patient, we're talking about $486,000 per patient every time there is one of these cases. So if you multiply that times 5 million, which are the cases of moderate to severe, we end up having a pretty good number. So that's why basically a lot of people are trying to invest in this field, because there is actually a need, and not only in terms of people suffering, but in our society nowadays, what counts is money, and at least this moves people and are trying to see if there is actually a solution for these patients. So some years ago, we ran an experiment, and it was a clinical trial, controlled study, double-blinded, And we have two groups of patients, and we use brain-machine interfaces controlling an exoskeleton. And after that, immediate after that, we used behavioral-oriented physiotherapy, basically trying to use the same movements that we used in the therapy with the brain-machine interface to generalize whatever we got to the daily living activities. And what we saw, it was actually that we saw significant improvements in clinical scale. In this case, was Fugelmeyer, in the group that got the brain-machine interface contingent feedback. That means that we had two groups. In the control group, the patients thought they were controlling the exoskeleton while they were moving it, but they were not. And in the other case, we linked the brain with the muscles. So whenever we detected that they were moving or they were trying to move, we moved them. And that's what happened. The recovery happened only in the experimental group, the ones that we linked the brain with the muscles. So this is how it looked like. This was 2007, so quite a long time ago. You can see here the brain activity online. 3 channels were used for feedback. This is the EEG cab, the amplifier systems going back to a laptop, the laptop controlling the robot. This was a rehabilitation robot from Motorica, an Israel company. And we detected here is the output, so that we were detecting, and then the patient basically was controlling the movement of that exoskeleton. So right after that, we did that also with a hand. Okay, where is this? Here we go. Sorry. We did that also with a hand exoskeleton, same idea. In this case, this is a patient from the control group. And then we had some physiotherapy, as I said, right after the session, in which we trained the same kind of task, opening the hand in this case, and then we were just trying to reinforce that with the patients, stimulating it, stimulating the tendons and the muscles involved in the task. And on top of that, we also did some functional movements, you will see it in a second, in which the patients were trying to use, for example, the reaching movement that you just saw training for a functional task. In this case was soup eating. And so this is an example of it. The patient just gets the spoon and tries to reach and go back, so that we generalize the results that we get. So basically we use the BMI as a priming tool for the therapy. It's not alone by itself, it can generate some improvement, but important is to use physiotherapy afterwards so that we can generalize that to daily living activities, and so that the patient, when the patients go home, the recovery is still, it's used for something so that it's retained. All right, so that was the physiotherapy, and this is the results. So this patient, for example, was about 6 years, completely paralyzed, couldn't move the hand at all, and these are the results. It might look very small, but these results are first movements after 6 years completely paralyzed, using only 1 month of training of the brain-machine interface coupled with physiotherapy. And below there you can see the Fugelmeyer results. We divided that into hand, upper arm muscles, and hand, upper arm muscles, and the combined upper arm scores for the Fugelmeyer scale. The change is not that great, it's not big, but at that level of impairment, the difference is huge. So just as an example of the functional results, I'm going to show you right now our patient that recovered the most. I have to tell you, this guy, when he came to us, he could barely move his arm and could absolutely not move his finger. So all of the patients in our study were completely at 0 with the hand, so they couldn't move it. So he recovered some flexion and extension of the fingers and could move it around, which normally would kick in spasticity, and then it would become spastic. In this case, the guy was very confident, so we gave him a heavier object, in this case a bottle of water, and he could just move it around, and what is more important, he could just drop it again and release it, so extend the fingers, which is where they have the issues. All right, so how is that translated to neurophysiology? Because it is great that this happened and worked, but we need to understand better what's going on in the brain, what's going on in the nervous system, and that's what we're what we're trying to do at the moment. So what we saw is, this is the case what normally happens when patients get a stroke. And you see the fMRI when they're trying to move, in this case the left hand, you will see a lot of activity bilaterally. So basically the brain is trying to recruit everything it has to be able to accomplish the task. And normally when they recover spontaneously, they end up having this pattern, which is actually what we managed to recover with our intervention, which is a lateralized activity of the brain. In this case, they're trying to move the left hand, so that you see right hemisphere activity. So that was basically a significant change in laterality index that we saw. But this is not all, because basically what matters is the EMG, which is at the end what is going to make the patient move. And what we saw is at the beginning, in the paretic hand, at no EMG, look at the scale, 10 millivolts, and here in the non-paretic hand is 100, and you can see easily how well they can contract the extensors in this case. And at the end of the training, we can see that that pattern is also in the extensors muscles that were paralyzed before the intervention. Although, look at the scale, it's still very small, 10 versus 100. But although that is very small, what we could do is actually use some machine learning techniques and decode that little activity that we see here. So this is before, and we can see nothing, so we don't decode anything. But here we decode, and here we see this little activity. We can decode it, and we could actually control an exoskeleton, for example, with that. So we recently heard something about muscle synergies. We also analyzed the synergies in those patients because we wanted to know exactly what's going on there in the muscles, if they are recovering, or how are the muscle synergies, because it was supposed to be the same, or published work before ours said that in stroke, more or less the synergies are retained. And it is to a certain level true, but not completely, not entirely. So we see here, for example, the different kinds of movements. The movement number 5 and number 6 are movements that are related to the hand, where are completely paralyzed. Sometimes they have a little bit of movement on the upper arm. And you can see if they have a little bit of movement available, the synergies are very similar between the healthy and the paretic side. But if you go to the more impaired movements, then there is a clear drop and there's a clear difference in muscle synergies. So basically what we see is here that the finger extension in the healthy side has a couple of synergies, it's very clear, but when we go to the finger extension in the paretic side, we saw a huge number of synergies. So what is basically happening there? If we go back to the separation between strokes, and if we think as the synergies as a cortical phenomenon, or at least that the cortex has something to do with the synergies, we see that actually in the subcortical stroke only, so when the motor cortex is not involved, the synergies are fewer than when there is a mixed stroke that is actually having the motor cortex involved. So, well, this is a very crowded slide, but basically this is a summary of the motor synergies, and this is in case of the mixed lesion. As I said before, there's like a fewer synergies, and actually they are more similar to the ones in the healthy side. But if you go to the paretic side, there's like much more synergies, especially the ones that have the paretic side. So this is lesion group with only subcortical lesion, and this is mixed lesion. In the mixed lesion, more or less, they are retained or similar to the healthy side, but in the ones that have only subcortical stroke and the cortex is there, it looks like the cortex is trying to generate new synergies to compensate the deficit, and that's what we see here. And actually, the shared synergies between one side and the other relates to motor impairment and is correlated to motor impairments only in the ones that have the subcortical stroke. Only. So how important is also corticospinal tract integrity? It's clearly nowadays everybody's using TMS to see the MEPs and see if actually there is a connection, and it is thought that the integrity of this tract will condition the recovery. And we can see here in a clear example, and the red is actually the healthy side, and you see the fibers, and in the paretic side, lesion side, you see a few fibers, sometimes you see none. And what we saw is actually that, and this is again the same study, but these are the patients in the sham group. Basically, they were not linked the brain with the muscles, and they didn't recover. But in the ones that we actually linked the brain with the muscles, anyway, they recovered if they got MEPs, their recovery was better, but if they didn't get MEPs, the recovery still was significant. So it is better to have MEP? Yes. But it is necessary for a recovery? No. So how relevant is cortex integrity? We also did some DTI analysis and found out something quite interesting, which is that we saw significant changes, but not what we expected to see them. So in the ipsilational side, we expected to have larger DTI or changes in DTI or FA values, but actually we saw significant changes in the healthy hemisphere. And actually they were changes that were decreasing the FA values, which means decreasing the different fiber tracts integrity in regions that are involved in inhibition. So what we assume here is that basically what happens is that the healthy hemisphere starts inhibiting less the lesion side, and that's why we got better. In terms of long-term results, what we saw 6 months after the intervention was that actually only the experimental group, and the ones that we linked the brain with the muscles, the Fugl-Meyer values still were retained, but still a bit lower, so probably in 6 months later it would have been gone. But 6 months after when they left the clinic, they still got significantly better than the control group. However, we saw that there is a clear influence in the lesion in the event-related desynchronization and synchronization, which is actually the frequency band that we use for our brain-computer interface. So if we see the mixed lesion group of patients, they get a way higher ERD, and if, well, way higher, I mean it's like less ERD, and in the subcortical group, they manage to do larger ERD, basically implying that the cortex integrity is important for the sensory motor rhythm, very important for the sensory motor rhythm. And the same happens for the beta band. So what is very important in these kind of trials is that we end up in a scenario which is not controlled as in a lab, because the patients are there, they're trying to move, they generate movements, compensate, so there are many artifacts that can influence the signals. And we just saw that when we are using the latest artifact removal algorithms, we can clearly see that the results change, and that the activity that sometimes is used is not the brain activity, but is more related to the EMG of the neck or eye movements. However, we can isolate that, and that's actually what we did. So we basically were very sure that we linked the brain with the muscles and not basically some eye movements on neck or cranial EMG activity. Right now, and this is more or less just starting to talk about the future perspectives, since we saw that many of our patients, approximately about 45% of our patients, had a little bit residual EMG activity, and we could decode it to, for example, 7 or 8 different functional tasks. This opens a new door, saying like, well, all right, it's great to use the brain and to link it with muscles, but if there is some muscle activity there, shouldn't we use it in the control? Shouldn't we reinforce the use of the EMG? Because that's actually what we want, right? The important question here is like, how do we reinforce this EMG? Because as we know, there are maladaptive synergies and wrong synergy patterns. If you reinforce the EMG that is not correct, you will end up reinforcing maladaptive synergies and patterns that you don't want. However, if you do that correctly, somehow, we think we found a way of doing that, mirroring, decoding from one side to the other. We build up a hybrid brain-machine interface that basically combines EEG and EMG activity, muscle and brain activity, to the control of the exoskeleton. So we recorded many activities. This is how it looks like. The problem of this is obviously the setup time. If you can imagine setting up the entire experimental design here, so with the EEG, in this case, this is a test in healthy participants, so we use 64 channels, but in a patient we will use 16 to make it faster. Then you have to basically also stick the EMG electrodes and stick the hand into the exoskeleton, which is quite a tiring process. So it ends up being at least 35 minutes of setup time, which for experimental time with patients is not very nice. This is how it looks, the setup. This is a patient using our setup. As you can see here, this is the EEG power activity on the channel C2 that we were used for feedback, and we're decoding that as a hierarchical classifier. So if there is an intention to move, then we jump into the EMG decoding, and here we can see some EMGs for different muscles. And as you can see here, this is the render of the decoded versus the intended motion. So this is right now the platform that we're using. However, we saw that maybe to induce a better plasticity and to be able to reinforce the operant conditioning, we needed something better for feedback. That means that we were able to decode the brain when they're trying to move versus not. But is that enough to induce plasticity? Well, we saw yes, but is that enough for like efficient and faster plasticity? So we know that if we have a microphone outside this room and we're trying to record what's going on in here, you're going to have to filter out a lot of noise from the street, etc., and you're probably not going to be able to understand very well what I'm saying. But if you place the microphone right in front of me, then you will understand perfectly well what I'm saying. The problem is that you just lose the big picture, right? So what is better? Right. So we think that maybe going inside the brain is a good idea. So we implanted one stroke patient with this technology, and right now we're working on the rehabilitation. This allows us to record the neurons next to the tip of the electrode, and with certain techniques, signal processing, we get kind of like a better idea of what is the intention of the patient. This is actually work that follows all the work that has been done in the US with this technology in the BrainGate trial, which basically have been published recently. These patients have a couple of these implants in the motor cortex and the sensory cortex, and with this activity of the brain, some neurons, some dozens of neurons, they are controlling, in this case, 7 degrees of freedom of this robotic arm, and in this case the same thing. Although this has local machine control, basically the arm is a little bit intelligent and knows how to grasp and etc., orients the hand towards the object. And in this case, they control functional electrical stimulation, surface electrical stimulation, with the brain activity. And then the last one, I don't have the video, but Ajiboye et al., they just managed to do that and close the loop with the brain activity, implanted brain activity, so intracortical activity, and also implanted FES in a patient. So this has been recently published. So where are we going, or where do we want to go, is something like that, in which we are going to have 2 phases, one non-invasive phase to get the patient basically adapted to the control of the exoskeleton. How does it work? How is it? The EMG control also, but basically non-invasively. And then a second phase, when this plateaus and you cannot get better, then maybe we just go and implant. And with that, we control, again, the exoskeleton and the muscle. So what we want is go from complete brain control, slowly building up muscle until we're in shape to move again. So this is how the setup looks like. The patient is here, has an implant, and she is controlling the 7 degrees of freedom exoskeleton. This is happening in the Basque Country at the moment. This is ongoing work. This is the people involved in this work, and I would like to thank them. This is how the signals look like. An important question that we had is how the signals are going to look once we implant in the cortex, if they're stable or not. Right now we're seeing great signals. Not all of the channels look like that, but in here you can easily see 3 different units that could be isolated and used in a decoder, and gives you enough information to be able to decode different degrees of freedom. How the decoding is and so on will come up later whenever we publish this work. This is just to give you an idea of how is this neurotechnology or brain-machine interfaces being tested at the moment. These are all the clinical trials ongoing, or at least registered, at least in 2016. These are all here based on EEG, and then we have here electrocorticography also, a couple of them, and this is the units that I just explained, the ones that have the intracortical electrodes. So quite a bunch of clinical trials, and it is needed. I mean, we need randomized, controlled, double-blinded clinical trials to prove that this technology works, but what we need more than that is to understand the neurophysiology behind that, and I think that is important. Otherwise, we would just like shooting in the blind. So we don't know what we're doing. We know it's working, but it reminds me to the beginning of the DBS. It was an accident, and it started to work with Parkinson, but nobody understood why it happened. And in here, the significant improvement is very little, and you don't know exactly why is that. So we really need to understand a little bit better before we say this technology is great, and we need to implement that in the standard clinic. So again, if we see the line of the neuroprosthetic history, hopefully in this decade we will see the eruption of neural interfaces in our day-to-day basis, maybe in stroke rehabilitation, maybe in communication, who knows. Anyway, let me thank all my colleagues that help me, assist me in my regular work. This is my team at the University of Tübingen and my team in Technalia, which actually we have support from Technalia Belgrade, from Andrej Savic, who's also working in the university here. We work with the university here and with Technalia Serbia, for example, in the electrodes, high density MG electrodes and functional electrical stimulation mainly. And thank you very much. This is my city, by the way, San Sebastian. Thank you.